announcements. First off, you will have a half class period lab next class. We're going to be working through measurements. So although we did an in-class activity last class where you were taking some measurements on a scale and reading the volume of a liquid, you'll be doing more with measurements next class. You will have a lab and it's going to be on density. Some of you are familiar with the concept of density, but we'll be exploring it next class. And so next class period, you'll have a bell work. After the bell work, I'm going to do a short lesson because I have to teach you density first. We're only going to go through pretty much that topic next class, and then afterwards I'll set you up with the lab. There will be 10 different lab stations set up at the 10 tables in the back, and then in the second half of class, you'll be doing the lab for the rest of the class period. I'll explain more of how labs go next class, but just be aware that that is coming up. In terms of a quiz, you can expect that you're either having a quiz, your first quiz at the end of next week, or the beginning of the week after. It's coming within a week and a half to 2 weeks. It is your responsibility to make sure you have a calculator by the time of that quiz, because most of it will be calculations based. As you've seen, our first topic is measurements. So make sure that you do have a calculator. You cannot use your cell phone as a calculator. It has to be a calculator. At the minimum, get a 4 function that's $1 from the dollar store so you can at least work with decimals. But it would be much better if you had a scientific calculator. Otherwise, you'll have to do everything by hand. And I don't want you to have to do everything by hand. So make sure if you haven't yet purchased one, get it done this weekend. Get a calculator, put it on the list of things you need to get. Scientific calculator. Unit 1, Intro to Chemistry. Lesson 2, Measurements Continued. So what we did last class is we learned about percent error, which you'll be analyzing in the lab next class as well. And we learned how to determine if a value in a measurement was considered to be significant or not. So what we're going to do today and where we're going to start is how do we round to a certain amount of significant figures. So go ahead and write how to round to specified, means we want this amount, sig figs. So that's the title, how to round to specified sig figs. And then I'm going to give you some steps on the side. You'll want to write those steps before you write the examples. Step 1, count sig figs left to right until desired amount and then draw a cutoff line immediately to the right of last sig fig. So that's step 1. Step 2 is to use the number or digit or value directly to the right to determine whether to round up or keep last sig fig the same. Rounding rules, at least at the high school level, lucky for you, are the same as they are in math. And so if you see a number 0 to 4, the value stays the same. And if you see a number 5 to 9, the value rounds up. So these are standard rounding rules, just to remind you of what rounding rules are. I'm going to give you some time to write down the steps, and then I'm going to illustrate the steps as we work through. So the purpose of this is when we are doing calculations with significant figures, and you have multiple different measurements, you will likely have to round your final answer. And so even back in the first lesson, we had to figure out, sometimes our calculator would give us some crazy number in percent error, like 5.59123598, and it kept going, and we had to know, hey, where do we round to? And so that we're going to address today officially. Where exactly do we round to in any situation? And so leading up to that, you first have to figure out how to round to a specific amount of significant figures, and then we're going to figure out when to round to a specific amount of significant figures. I'm pausing to give you a little bit more time to write the rules. Once you're done writing the rules, you should write the first example. Then I'm going to start explaining in about 30 seconds. I'm giving a little bit more time. And so for this specific process, you don't need a calculator yet. By the end of class, you will need a calculator, at least the decimals. Okay, so it's been 30 seconds. I'm going to go ahead and start explaining with the example. It says round off each measurement to the number of significant figures that's shown in parentheses afterwards. So when you look at A, it tells you that the value is 314.721 meters, but that we need to round it at 4 significant figures. So we only want to round it to 4 significant figures. And so the steps, you count values starting at your first significant figure. So you count your values starting at your first significant figure, to be clear. And so is 3 a significant number?
Yeah.
Yeah. So we're going to start counting there. So that means that this is my first, this is my second, this is my third, this is my fourth, and then following the rule, I do this. I write a line. Now, I'm going to rewrite it just to give myself some space. And the question is, when rounding, do I keep the 7 a 7, or does that 7 turn into an 8? And what you're supposed to do when rounding is you use the number directly after the last number you need to count in order to determine if it rounds. And so does that 7 stay a 7, or does it turn into an 8? It stays a 7. Because if you think about it, 72 is closer to 70 than it is to 80. That's the idea. So when you round it, it's 314.7, and then you keep the unit. You measured meters, so it's 314.7 meters. It's the same number expressed to 4 significant figures. In mathematics, when you were taught rounding, pretty sure you were taught to round to the nearest 10, to the nearest 100, to the nearest tenths place, to the nearest hundredths place. We don't express how we round in that way in this class because we work with measurements. We express how we round the amount of significant figures instead. And so let's take a look at B. A was the simplest scenario. What I always do when I'm teaching is I'll show you the easiest example first, and then we step it up a notch and we step it up another notch. Yes.
I have Ethan Thomas Mitchell.
Ethan, yes.
Ethan?
Yes.
Thank you.
Okay. So, following the rule, you count your significant figures left to right. Is the 0 significant? The next 0 is significant? So the first significant figure there is the 1. So you start counting here. That's 1. And then your second significant figure here is the 7. And then you write a cutoff line right there. Everything here needs to be written. Those zeros, even though they're not part of the measurement, they need to be written because they're telling you how small your measurement is. They are there to indicate how small this measurement is. So now that I know 0.001775, there's my cutoff line. I know I write the 0, I know I write the 001, and you have one decision to make. Does the 7 stay a 7 here, or does it turn into an 8? We have to use this number to determine, and this is where we look at rounding rules. The number 7 is a value greater than 5 or greater. So that means that this 7, does it stay a 7 or round up?
Rounds up.
Rounds up. So 0.0018, and that'll be meters. So that was the second scenario. You had to start counting at your first significant number. That's what I wanted to point out. It's not always the first value that's written if that value isn't significant. And so example C, this is the one where if a mistake is made, it's usually made here. 8,792 meters. We want to round this to 2 significant figures. Does the 8 count? That's significant. The 7?
Yeah.
But that's it. That's all the significant numbers we can have. So we write a cutoff line here. And so we have 8,792. We want to express this in 2 significant figures. So we write the 8. Does that 7 stay a 7 or turn to an 8? Turns to an 8. And is that it? Am I done?
No.
Does 8,792 round to 88?
No.
You would be shocked how many times I see a student writes that. It does. But it doesn't. You're absolutely correct. What you have to do if you come across the scenario that there are less significant figures than the size of the number is you have to fill in zeros until you reach the ones place. And so the idea is that you have to fill in zeros until the ones place, because it needs to be a whole number. And it needs to be as large as the value is. So it would be 88, and then you put in 00. One more important question. Do you put a decimal there? Yes or no? And this is the trick about last class. If I put a decimal there, I say that those zeros are significant. Do we want to say that those zeros are significant?
No.
No, they're just there to hold how large it is. So it's actually just 8,800 meters with no decimal. Yes, we are that picky. If this is communicated 8,800, it means this is rounded to 8,800, which we know it is because 8,792 was rounded to 8,800. And so it communicates this is a rounded value, not an exact value. If you put the decimal there, you say it's an exact value, and that would be a miscommunication here. And so that's the thing. In chemistry, you're going to find out we are really picky about what appears to be tiny things, but they're not. When you get to see later on how small differences can actually make big differences. All right, so this is the first thing you needed to learn, which is basically just how to round to a specific amount of significant figures. It's the same idea in mathematics as rounding. It's just instead of using round to the nearest 100, round to the nearest 10, we now say we want to round to a certain amount of significant figures in a measurement. So that was number 1. We're going to go to idea number 2 that we need to know for the day. And this is a review, or it should be a review for everyone. Based on the baselines, some students knew how to do this, some students did not. And so our second topic is going to be scientific notation. Because not everybody knows it or remembers it, I have to reteach it so that you are comfortable with looking at scientific notation and working with scientific notation. And so this is the structure. You may want to write this down, what you see in this picture here in your notes. You do not have to write the left part. That's just additional information like it would come out of a textbook. So this is the part that I would like you to write. The structure for scientific notation, and you should write the title scientific notation so you know what it is you're talking about. You always have a single digit 1 to 9. That's what the letter C is representing. So it's a single digit. Followed by a decimal and however many significant figures you have. And then you multiply by a base 10, and you raise that to an exponent always. The exponent has to be an integer, which means it's a positive or negative whole number. And we'll address how to change into scientific notation and out of scientific notation. I'm giving you a little bit of time, and then I want to address when would we use scientific notation? Why would we use scientific notation? You got a computer here. You may have a little bit of context for what I'm about to say, because last class I gave you a scale and I asked you to measure a small piece of paper, if you'll recall. And that small piece of paper weighed somewhere between 0.1 and 0.8 grams, so less than a gram. In chemistry, we look at elements, we look at compounds, and the thing about single elements, if I have a single atom of an element, it's really small, like really, really small. 1 gram of the element hydrogen, 1 gram, which is a little bit heavier than the size of the piece of paper I gave you, which is really light, right? It's a really light mass. 1 gram of the element hydrogen is that many atoms of hydrogen. That's a lot. And you're not going to be able to count atoms in this class. Absolutely not. Can't see them. They're too small. You're not going to be able to count them. But yet we know that there's a lot of them. And so if I need to say an amount of how many atoms I have, I'm going to need to express it in scientific notation. Because you don't want to write 602 followed by 21 zeros, and I don't want to read that. And if you were to take a Cambridge exam, a Cambridge examiner would not want to read that either, and they just wouldn't give you the mark. And so the question is, when is the rule of thumb to use scientific notation? And so it's going to be for values larger than 10,000 or smaller than 0.0001. So about like 10 to the 4th and 10 to the negative 4. After, you can write 3 zeros, but once you get past that, it starts to get grainy in counting zeros, and our eyes get crossed. And we're like, I don't want to count zeros anymore. So whenever you have what's considered to be a very large number or a very small number, instead of writing in standard form, which is just writing out the number, we write in scientific notation. Sometimes in this class, we will need scientific notation, so we need to get comfortable with writing in scientific notation. This is an example for the same number, how it would be written in scientific notation. There's one more thing to know. When writing in scientific notation, you do not change the amount of significant figures. So you're going to want to make that note before we start examples. When writing in scientific notation, you want to keep the sig figs the same. Keep amount of sig figs the same. You're just changing the format of your answer. If you look at these two values again, 602 with 21 zeros, how many significant figures are here? In this gigantic number? 3. Because we don't know these zeros are exact. We only know to precision the 6, the 0, and the 2, and the rest is implied to be rounded. When you write this in scientific notation, guess what? You also write 3 numbers, 3 significant figures. And so you keep the amount of significant figures the same when you are switching between regular standard form and scientific notation. So now we know when to use. You've got the structure. We're going to take a look at a couple of examples and we'll go over the steps. I'm going to show you some pre-printed examples first, and then we'll create some from scratch. So here we go. These are some just pre-done examples for you. You'll notice that 4,500, what you do is if you have to move your decimal point to the left, you end up with a positive integer. So always moving your decimal to the left results in a positive exponent. And so here, if there's no decimal, you put it at the end of the number. Just for the purposes of getting scientific notation, you moved it 3 spots from the end of the number to right in front of the 4. And so because you moved it 3 spots, the exponent is 3, positive 3. This is standard form. And this is scientific notation. And these are both the same exact value. Now, 10 to the third, what is that? A little bit of math here. What is 10 to the third? 1,000, right? It's 10 times 10 times 10. So this is actually 4.5 times 10 times 10 times 10. If you were to put that in any calculator, you would see that it would work back out to be 4,500. These two are the same exact value. And so the reason I bring this up is to recognize if you see a positive exponent, this means you have a large number. Positive exponents always indicates a number larger than 10 or a value larger than 10. Which means, what do you think a negative integer or a negative exponent means? Very small. A very small number. And so if we look at the bottom scenario where we move the decimal to the right to get our exponent. Notice if you move to the right, moving your decimal right, results in a negative exponent. Negative exponent. And if you see a negative exponent, means the number is smaller than 1. So you could actually look at the exponents in scientific notation, and you should have an idea of how large or small your actual value is in standard form. If you see a positive value, it means large. And if you see a negative exponent, it means small, smaller than 1. The reason we use base 10 is because you can move your decimal to the left or the right, and it adjusts the value as a result. It's the same reason when I teach metric system, we'll also be moving our decimal to the left and the right to go between different units. I'm giving you a little bit of time. These are the pre-worked examples, and then we're going to take a look at some ourselves. I'm moving forward in about 20 seconds. If you need to take a picture, this would be the time to do it. I did not finish writing out what I put there. All right, we're going to go ahead and continue now. So this is practice. And we are going to practice with writing each number in scientific notation and taking each number out of scientific notation. So let's go ahead and go through the steps for scientific notation. And some of you will be more familiar with this than others. I just want to make sure we're all on the same page. So step one, you will need to find or place decimal point in the value. So you find or place a decimal point. Then step two is you have to move the decimal immediately to the right of the first non-zero number. And then if you move to the left, it's a positive exponent. And if you move to the right, it's a negative exponent. And then the actual value of how large or small the exponent is how many spots you move. So let's give the direct instructions here, and then we'll take a look at this with the example. Then we'll go backwards. There is a shortcut to scientific notation on the calculator, but more than half the class doesn't have it yet, so it's not worth going over. However, if you want to stop by after school and you have the proper calculator or during homework classroom time, I can show you a trick to not have to do scientific notation manually. All right, so I'm going to start working through step one. Step one, find or place this. It's here. So found. Next step, move the decimal immediately to the right of the first non-zero number, which means I'm going to move my decimal right here. Then you're going to rewrite the value starting with that first non-zero number, which is 2, and then all the other numbers trail. So it becomes 2.044. Multiply by 10. So I'm just following the format. The format, remember, was some kind of number multiplied by 10 to some kind of exponent. That's the format for scientific notation.
And then -2? Yep.
-2. Correct. Because I move my decimal to the right, I know that it's going to be negative, or you can reason it as because I know this number is really small. My exponent has to be negative. And it's -2 because I moved my decimal 2 spots. So this is 2.044 times 10 to the -2. Notice how I kept the amount of significant figures the same. 2044 is 4 significant figures. And 2.044 times 10 to the -2 is also 4 significant figures. So I've kept the significant figures the same. When I change this to scientific notation, the zeros that were holding how small the number was, they just disappear because they actually weren't significant in the measurement. So when changing to scientific notation, insignificant numbers drop off, actually. B, let's go through this again. So find your decimal. If there was no decimal there, where would we put it? Just, we would put it at the end to make it a whole number and then move it. So there is a decimal here though. So we're gonna locate that decimal and then move it to the immediate right of the first non-zero number. So in order to do that, we have to move it this direction to the left. So then we rewrite the number starting with the first non-zero digit, and then you write your decimal and everything else that's significant, which is everything here. And then you do times 10. Is my exponent positive or negative? Positive. And how many times did I move my decimal? 4. So it's positive 4. That's it. Now, what about taking numbers out of scientific notation? You move it the opposite way. And my strategy is to look at the exponent to see if it's negative or positive, because that tells me if the value is large or small. Lefts and rights were confusing to me when I was younger. They can still be confusing now. I know for some of you, it's probably left and rights may be confusing. So another way to look at it is, this is a small value. If I see a negative exponent, it means it's a small value. That means that it's a number smaller than 1, specifically. So which way do I need to move my decimal to take it out of scientific notation?
Right.
It would have to go this way, so that the number ends up being smaller than 1. I'll do those lefts and rights will always mess you up. 1, 2, 3, 4, 5. So 5 spots, and you have to make the number smaller in standard form. So it's going to be 0.0000366 in standard form. And then for the other one, B, 7.56 times 10 to the third. This is a positive exponent, so that means it's a larger value, something larger than 10. So do I move my decimal to the left or the right to restore the number in standard form?
Right.
To the right. So it's going to go 1, 2, 3. And it would be 7,560. Do I place a decimal, yes or no? Good, we're getting there. So this was 3 significant figures. So my final answer must also be 3 significant figures. If I put a decimal there, I change it to 4. And we're not changing the amount of significant figures when we're changing formats. Yes.
What if it was 7.50?
That's a good question. And what could you do in that That's actually why it's preferential. If you had a situation like this, it's actually preferential to write your answer in scientific notation, because it'll be very difficult to tell in standard form that 1 0 was significant but not the other. But what you could do is you could say 7,500, and you could just put a little line above the 0 to say that that 0 is significant but not the other. So you could do that. Typically, we would actually, in that specific scenario, keep our answer in scientific notation, actually, because it shows which 0 is significant. All right, we're going to move forward. We've done rounding. We've looked at scientific notation. You will have homework on that. And we have one more scenario to encounter. And actually, depending on our timing, you may have some time during class to work on classwork and homework today. My goal is to try to give you some time in class to work on it so that you don't have to take everything home to do. So if we can get through our next topic well, we should be good to go for being able to work during class instead of having to take what you have to do as homework. Here we go. The last section of today's lesson is how to perform calculations with multiple measurements. So this is the final topic, but it is a large one. It's the largest topic of the day. When you are performing operations, and what I mean by operations is addition, subtraction, multiplication, and division, and you'll have multiple measurements, you have to consider the amount of significant figures of each measurement. And so go ahead and write this down, write down the rule. I'm going to bring up a guiding principle, and then we'll go over how to analyze. Significant figures in multiplication and division. What's the rule? And then when, how, why do we apply this rule? Multiplication and division is used about 90% of the time in this class. Most of the math we do in this class is multiplication and division. So therefore, the rules for multiplication and division are the rules we're going to apply the most often. If you have multiple measurements and you're multiplying or dividing them, in order to round, you have to recognize that you can only be as precise in your final calculation as your least precise measurement. So there is a guiding principle here. I'll write it. The guiding principle of these rules, why they're there. The guiding principle is your final calculated value can only be as precise as your least precise measurement. You can't add additional precision if you don't have it. So this is how these rules came about. We have to round to our least precise measurement. So you may want to write that down because it is the reasoning of why. When you multiply or divide, and it doesn't have to be just two values. It could be you multiply two values, three values, four values. Like you could have 3.5 times 1.82 times 3.7, continue. The idea is that the amount of significant figures of your least precise measurement is gonna be the amount of significant figures of your calculated answer, because that's the amount of precision that we know. And for multiplication and division, this ends up being the lowest amount of significant figures in the value. And so that's going to be the key guideline here. So get out those calculators. They don't have to be fancy. You just need a calculator. You'll notice that the numbers here are easy to work with a calculator, but I don't want you to do it by hand. Multiplying decimals is yucky. By hand. All right, so let's take a look at what we need to do. And I will go ahead and write out steps just so that you can follow along with me. Step one is you count sig figs in each measurement. Let's take a look at A as an example. So count sig figs in each measurement. Step two is going to be round final answer given in calculator to lowest sig figs. So take a look at A when you're ready and apply step one, which is to count how many significant figures are in each of those measurements. 7.55 has how many significant figures? We know the 7, the 5, and the 5 are all significant, so it would be 3. So this is the way that we're going to evaluate. I just write it at the top usually. 3 SF, 3 sig figs. Then take a look at your other value that you're multiplying, the other measurement that you're multiplying. 0.34. Is that 0 significant?
No.
But the 3 is.
Yes.
4 is. So altogether this is 2. So the way to evaluate this is you compare, okay, that measurement has 3 significant figures. This measurement has 2 significant figures. My final calculated value has to be only 2 significant figures. So you can only be as precise in your final answer as the value with the least amount of significant figures. So that means that your final answer should be rounded to has to be 2 SF. It has to match your lowest amount. And so what would the next step be? Well, plug those values in the calculator. Do 7.55 times 0.34. Let me get my calculator. 7.55 times 0.34. So my calculator gives me, and I'll write out what the calculator gives, but that's actually not the final answer. So it's going to be calculator gives me 2.567. But if we write that, you put that in the bell work, you put that in a homework, it's going to count you wrong. Why? Because the whole point is we have to round this. If I just, say multiply and give what my calculator gives me, I'm not teaching you anything at all. We're learning how to round these measurements. So you would round after which number? How many significant figures? So after the 5. So it's going to be 2 point. Does that 5 stay a 5 or move to a 6? We learned this at the beginning of the lesson. It goes to a 6. And now you see why it's asking you to round to a specific amount of significant figures, because that's the rule. 2.6 what? No 0. Unit. So, yeah. Let's review that real quick. So there is actually an Algebra 1 prerequisite for this class. Meters times meters is this situation. You've got meters to the first, you've got meters to the first. If you multiply these two units, what do you have to do with their exponents? Multiplication indicates? Add. So you get m to the 1 plus 1, which is m to the second. So your unit here, you either can write full meters squared, or you can write m squared. M is the shorthand for meters, the abbreviation. Either is acceptable. But yeah, you do have to recognize how to multiply units and divide units, which I'll show you in a little bit. So the final answer here is 2.6 meters squared. Let's take a look at the second example, following the rules. How many significant figures in 2.10? Evaluate that first. How many significant figures in 0.70? It would be 2. So what I usually do is I just circle the lower amount because I know that my final amount has to also have that same amount of significant figures according to my steps. So I need to round my final answer given in the calculator to the lowest sig fix. In this case, that's 2. Now we plug the values in the calculator. And my calculator gives me 1.47. So calculator gives me 1.47, but that can't be my final answer. What's my final answer? Right. So I know 2 significant figures, so I cut off after the 4. And I use the 7 to tell me if the 4 stays a 4 or turns into a 5. It turns into a 5. So it's 1.5. Same situation, meters times meters is? Squared. Meters squared. I have a question before moving to the next one because I asked this in the other class periods and I think you all can handle it as well. If you are measuring meters squared, that measurement, what are you actually measuring?
Area.
Yep, you're measuring area. Meters itself is a length. If I have a length times a width, that's an area, right? And what if you had, because this is going to have to do with next class's lab, what if you had meters times meters times meters? What would that be measuring? A volume. We'll be measuring volumes as part of what we do in next class. And so that will come up. All right, let's take a look at C. Same steps for multiplication and division. Count how many sig figs are in each number. 2.4526 has how many?
5.
5. And 8.4? 2. The lower amount between 5 and 2 is?
2.
So our final answer will be rounded to 2. Then you perform the operation, which is basically just in your calculator, divide the two numbers. In the order that you see here. You should divide the two numbers. You get, calculator gives you some crazy thing, like 0.2919769. Do I expect you to write that all down?
No.
Could you just round it off reading it on your calculator? Sure. Right? You could just read it on your calculator and be like, okay, what's your second significant figure there? In this calculation, 0.29197619. What's the second significant figure? 0 is not significant. So the 2 is the first one and the 9 is the second. So that's your cutoff line. So you could read that directly off your calculator. I don't expect you to write down all the numbers off your calculator. So this would be 0.29. And what's the unit?
Meters 3. Exponent
Well,
3.
be careful, because instead of a multiplication, this is a
Oh,
division. And
subtract.
so, yes, exactly. So if I've got meters squared divided by meters to the first, just to review real quick where this applies into math, if I'm dividing, that means I'm doing what with the exponents if the base is the same?
Subtraction.
So it's m to the 2 minus 1, so it's m to the first. And so our correct unit here is actually meters. And are you expected to write units in this class? Yes, all your answers should have the correct units following them. Last example for this exercise with multiplication and division. 0.365, how many significant figures? 3. 0.0200, how many significant figures?
3.
What is less, 3 or 3?
3.
They're the same? So what would you do if they're the same? Just 3 for your final answer. Don't stress. It's going to be equivalent to your lowest amount of significant figures. If you've got the same, then your answer is also going to be 3 significant figures. So now you're going to do 0.365 divided by 0.02 in your calculator. And your calculator gives you 18.25. We only want to write 3 significant figures, though, because that's the amount of precision we know for sure. And so we cut off after the 2.
18.3.
And it would be 18.3. And it's the same situation as the last one, so the unit would be in meters. Yeah, n to the first. All right. This rule you've got to master. You have to master this rule because, like I said, during the class, 90% of the math that we do is going to be multiplication and division. And every time you're going to have to round to the correct amount of significant figures. These are the rules we use to round as we're working through the math component of the course. And so there's one more set of rules, though. There's not only multiplication and division you could do with measurements, but there's also addition and subtraction. And although you won't see addition and subtraction as much, you'll actually see it in the lab next class. So we've got to review how to add and subtract to the correct amount of significant figures. So I'm going to leave this up for about 20 more seconds, and then we're going to go to that rule. Then we'll have one more thing to do, which you'll either want your scientific calculator for or a tab open to the Desmos, because we have to address how to do exponents in the calculator. All right, so last set of rules is for adding and subtracting. And so adding and subtracting, and then we haven't approached scientific notation yet. So it's adding and subtracting with significant figures. And then we'll take a look at scientific notation for the last part. When you're adding and subtracting, your rule is similar, but it's not exactly the same. So make sure you write it down. We have to analyze it slightly differently. The guiding principle is the same. You can only be as precise in your final calculation as your least precise measurement. But when you are performing an addition or subtraction, instead of counting the total amounts of significant figures, you look at the decimal places of each value. And I'm going to explain why shortly. So your answer is going to be rounded to the measurement with the least precise value, which means least amount of decimal places. Some of you will just memorize that and get the answer super quick, but I'm going to develop some understanding of why in a little bit. Write it down first, though, and then I'll use the examples to explain why. To explain why, I'm going to remind you these are measurements. If I have to add or subtract measurements, what's going on? So adding multiple measurements. And once again, this is only not for 2 measurements. It could be 3, 4, 5. Usually just a couple of them. 10.185 plus 3.2 liters. How do we know where to round? Why do we know where to round here? So if we just read the rule, it says you're going to round to the least amount of decimal places, which means you count how many values there are after the decimal. For the first measurement, you should see the 1, the 8, and the 5. That's 3 values. That means we know this to the thousandths place, technically, right? We know that to the thousandths place. 3.2 liters. What do we know that number to?
The one.
I call it the 10th place. But it's only to 1 decimal place. I'm putting a little guide of what I mean here. 1 decimal place, 3 decimal places. So if I just blindly follow the rule, I know that my answer is going to be rounded to 1 decimal place. But I don't want to just blindly follow the rule. I want to understand why the rule is what it is. Let's revisit what I brought up last class period. If you've measured 10.185, that means your measurement device, you were able to measure with that amount of precision. So definitely what's happening here is you had 2 different devices. One measured to a greater precision than the other. So the number that follows the 2 in the measurement 3.2 wasn't written because it wasn't measured. We didn't know it. Whatever device we had wasn't good enough to give us more numbers. So the question becomes the following. If there's no value written here, can we just assume that it's definitely a 0? Yes. We don't know what it is. So what I'm going to do here is I'm going to write a little question mark. I don't know what that is. I don't know what that is. Which means I don't know what this 5 is plus. And I don't know what that 8 is plus. Which means those numbers cannot be used in your final answer. Which is why an easy way to look at this is just to look at where your numbers match up. And the last place they match up, you write your dividing line. And that tells you where your cutoff point is. So 1 decimal place is what it ends up being. When you add, you can use your calculator. You do not have to do it in your head, but if you want to do it in your head, you can. There's no calculator in the shame. No calculator shame in this class. You can always use a calculator. So I've got 13.385. But how do I express my final answer rounded correctly to the amount of significant figures that I know for sure? It's going to be 13 point. Does the 3 stay a 3 or move to a 4? So it's 13.4. And I can't say I know what those numbers are. So that's why my cutoff's right here. And it would be 13.4 liters. Because when you add or subtract units, the units don't change. It's the same idea for those of you who like math. If you have 3x plus x, what is your final answer here? 3x plus 1x is 4x. You don't change the variable when adding numbers in front. The same thing's going on with units. If I have liters and I add liters to liters, my final answer is still in liters. All right, let's take a look at the second one. 14.68 minus 5.1. The rules for addition and subtraction are exactly the same as each other. (14.68 minus 5.1). now that we got that idea from the last one, in 14.68, where would I write my cutoff line?
78.
Right. Because there's no number here, so we can't say that that's significant in our final calculation. So wherever there's a missing value, you can't include it in your final answer. So we only know the degree of precision for both to the nearest 10th place, or 1 decimal place. And so really, you don't have to draw this out every time, but for those of you who need to see it visually, I do encourage you to do so. If you just understand from the words and you just count the decimal places and say, this is 2 decimal places, that's 1, so my answer is 1, you can do it that way. I'm just giving you a visual format to help you understand. So 14.68 minus 5.1, let's go ahead and do that calculation real quick. No calculator shame, and it's early in the morning, so definitely no calculator shame. And much easier to make mistakes early in the morning when we're not fully awake. So I get 9.58 in my calculator, liters. And so what's my final answer here?
9.6.
9.6. And I can't include this because I don't know what that number is. So 9.6 liters is my final answer here. All right, so we have one more situation to cover today that's really, really important. A lot of these initial lessons is just getting you set up for success later on in the year, making sure you understand how to work with measurements, making sure you know how to work now with exponents, the final thing. So once again, at this point, if you have a calculator, or I'm letting you borrow one of mine, you're going to want that out and ready. And if you don't, then make sure you have a tab open to Desmos so that you can at least for your homework have something to work with so you can get the correct answers. Yes. Question? Question? Xavier? Go ahead. All right, so last situation that I want to bring up is multiplying and dividing with scientific notation. Just come back in 10 minutes. So write it down, multiplying and dividing with scientific notation. Get your calculators out. This is something you could do by hand, but I don't encourage it because it's really not fun to do by hand. So the question is, if you were given your numbers in scientific notation instead, how would you write your final answer? Also in scientific notation. So using the TI-30X calculator, I am going to teach how to do it here, and then afterwards I'll pull up the decimals. If you have the proper calculator, I think you can also do this in the Casio. You're going to want to learn how to use your exponent in the calculator. You're going to use exponents all through this class. I told you that 1 gram of hydrogen is 6.02 times 10 to the 23rd. Atoms of hydrogen, you're going to have to work with those numbers on a calculator. So here we go. Here's what you enter. This is a multiplication. So you enter in your calculator. Enter 3.0 multiplied. Then you find the 10 key. This is what's important. The exponent key in your calculator is this little arrow up. That's the proper one to use. There's other ones, but this is the one you're going to want to use. You can find that little arrow on the left-hand side. If you've got the calculator, you should start entering in the numbers so you're following along. Then, to make sure that your exponent is negative, you have to use the negative key. The negative key is actually right next to enter. It's in parentheses. And then the number 2. Multiplied by 1.33 times 10, exponent again, negative 5. You should also be able to enter it if you don't have the calculator. You can use the Desmos. See if you can use whichever device you can use. The answer the calculator gives is 0.005. 0, 0, 0, 0, 0, 3, 9, 9, which in scientific notation is 3.99 times 10 to the negative 7. I believe the Desmos will actually just give you 3.99 times 10 to the negative 7. So if you have a calculator, you should be attempting to answer this in the calculator. If you get a syntax error, let me know, and there's no log. Log stands for logarithm. You logarithm. Yeah, you should not press that. The one you're looking for, 3.0 by 10, that's the exponent. That little, that's the arrow up. No. You got it. Yes. Okay, so that means you subtracting, not the negative. That's also negative. All right, let me know if you are not able to get the answer, the same answer I have. That is not it. 3 times 10. That is the arrow up. You have to follow exactly the button I wrote. That is the arrow. And then you keep going. You write everything in the order. Times 1.33. Times 10. All right. If you are not getting the right answer, show me your device. Did I give you that? All right. Yep. It's in scientific notation because I taught the classes yesterday how to do it with the calculator, so I'm doing it back. There's a mistake. This doesn't say 1.33 multiplied by 10 is 5. You did 1.33 minus 10 is 5.
Yeah.
So change that to multiplication. Now, it's two different amount of significant figures, but it's the same answer. All right. Did you get it? Yeah, that's it. It's just the way it is, 3.99 and then the 10 to the negative 7. You're gonna have to recognize that your calculator does it like that. Yes. That says plus, not multiply. You'll probably need to use this. X to the box where you plug in the number.
Do I have to round it? Because it's really.
Because you don't.
Do I have to round it to?
You will have to round your final answer to the correct amount of significant figures, yeah. So that's not the final answer, that's actually the one my calculator gives me. I still have to round it afterwards. Hold on. I believe you would go here. Because you don't have the TI, it's a little bit different, but I believe that's the button you have to press. The X to the something. Yep. All right, so just to say a couple things. First of all, if you got this in your calculator, good, but we still have to round it. How many significant figures? 2, because this is 2 and this is 3, so your final answer has to have 2 significant figures. So rounding it to 2 significant figures, it's going to turn into 4.0 times 10 to the negative 7. So that would be your final answer here for the first one. What I'm going to do is I am going to get out of this screen to show you the Desmos. If you are struggling with your calculator, at least to do your homework, or you don't have the proper calculator, at least to do your homework, I'm going to pull up the Desmos. And then just, it's the same operation. Can I look at yours? Because I can't look at the screen at the same time as looking at the decimals. No, just what's your, so it's 3.0 times 10 to the negative 2. You start by putting the fraction bar because it's a division. So if you're using the decimals, you would do 3.0. Why delays on here? So that's the top, 3.0 times 10 to the negative 2. And the bottom would be 1.33 times 10 to the negative 5. That's the same time yesterday. It's a multiplication times 1.33 times 10 raised to the negative 5, like that. And there's the answer from your calculator. So if you look here, I'm also sharing the screen. You should see the correct operations in decimals. Yes. You got to get the hall pass from the front. All right, let's take a look at the second one. There you go. Just come back in 10 minutes. All right. The first one was the easier scenario. The second one's actually more difficult to enter the answer in. If you have a division. Oh, and by the way, with that first one, it was 4.0 times 10 to the negative 7, right? What was our units? Centimeters times centimeters. So it's actually centimeters squared, just to make sure you have the right unit in your answer. Taking a look at the second one. This right here, whenever you see it, means division. Whenever you see the backslash, that always means division. And so this means that the scenario that you actually have is 7.1 times 10 to the negative 2 meters squared divided by 5.00 times 10 to the negative 3 meters. When you're using a calculator, whether you're using your scientific calculator or you're using the decimals, your scientific calculators were devised to follow PEMDAS. You all know what PEMDAS is, right? Parentheses, exponents, multiplication and division, addition and subtraction. So here's the problem. If you enter everything in your calculator, this times this divided by this times this, your calculator will actually misinterpret and it'll multiply this last exponent instead of divide it. And you'll get the wrong exponent as an answer. So you have to be careful. When you are utilizing a calculator to solve with exponents, you need to make sure to put parentheses around the whole denominator. On the decimals, you would just make sure everything is on the denominator. And so I'm going to give you the series of buttons again to push if you've got the correct calculator. It would be 7.1 times 10 raised to the exponent of negative 2. Then you press division. And then around your whole entire denominator, you put parentheses. So there's actually a key for parentheses, opening a parentheses in your calculator. And then you would have that. So see if you can enter this in your calculator. I'm going to write the answer you should get if you did it right. If you don't have the appropriate calculator, then at least do it in the Desmos to see if you can get the right answer. I'm going to write the calculator answer is 14.2. So check to see if you get 14.2 in your calculator. If you need help or you get something that's a syntax error, let me know and I'll see if I can troubleshoot. Today's for figuring out how to do exponents in your calculator. So check to see if with whichever calculator you're using, that you can get the answer I have up on the screen, which is 14.2. Weird. So this log thing is a problem. That means you've entered a logarithm function, which I think it's just this function pretended it has. But that's not. Oh, the same thing happened in the first one. Okay, so that log. Okay. That's what's really nice. So we calculated by counting, look at what you did and see what happened. I think that was the first one. That was the first one. You guys know. So the exponent's off, which means that it misinterpreted as a multiplication instead of a division. When he comes back. Check to see in your calculator. If you do not have the appropriate calculator, the TI-30X or the Casio, then you should be solving on Desmos to make sure you can get the right answer. Type it in the calculator. Let's see. Yeah, do that. Did you get it in the Desmos? Yeah. You have it here? Perfect. All right. Welcome back. When you get to the homework, you are going to have to figure out how to use your calculator appropriately, or you're going to need to use the Desmos calculator. I think what might be, let's see. Do you have a negative key? Yeah, you're using subtraction instead of minus is what's going on. Oh, go ahead, the hall pass is up there, the orange hall pass. The negative key is right here on your calculator. So you have to delete the subtraction sign and change it to negative. That's where the answer is. Okay? Anybody else with calculator troubleshooting before I don't know that one. Before I move on. If you struggle with the calculator, once again, you are going to have to pick up on it. You have to basically, I have to show it on the Desmos, so just do the second one. 7.1 times 10 to the negative 2 divided by, it's the same as that in the order I wrote it, times 10 raised to negative. see if you can redo it and see if you can fix it. Yeah. This is the one. So you shift and then that to go to the flowing. You're welcome. Did you delete it for both of them though? Yeah. Because there were two.
And then I rewrote it.
Where are you doing exponent? No syntax error. So I don't know. I don't know what's going on. All right, 14.2 is the answer you should get. I'm going to go ahead and see what this is in the Desmos for those of you that are not with the appropriate calculator and you need to do your homework anyways. Let's take a look at what this looks like in the Desmos. So now we're going to want to use the fraction bar to indicate that there's a division. So we'll do that. The top number is 7.1 times 10. To do the exponent, my suggestion would be to use the caret, which is the shift 6 on your calculator. If you do shift 6 on your calculator, that puts whatever you're about to place in the exponent. And then I would put my -2. That gives me the top number. So to get the exponent, once again, I do shift and then the number 6 in that order. And then for the bottom, same thing. So it's going to be 5.00 times 10 it's a little laggy. To the, and that's -3. And then if you did it right, you get 14.2. So check to see if you weren't able to do it in your calculator, if you can at least do it in the Desmos calculator. You need to be able to pick up how to get the right answers with exponents. And that is something that I would like you to learn now. This is the last part of the lesson.
Because the exponents.
Mhm. That's a great question. Let's take a look back at what we have here. I told you that from the calculator, the answer you get here should be 14.2. What would the unit be? Right. So it's m squared, and I told you that it was divided by meters. So you got to do that thing where you do m to the 2 minus 1 with the units, so you get m to the first. The exponents here, for scientific notation, have nothing to do with the units. They are attached to the number in front. So it's really evaluating these. The division, so you subtract to get your final answer. Now, this actually isn't rounded correctly. All we did was get the answer in the calculator. How does this get rounded correctly?
It's 14.
Right. So this is 2 significant figures. This is 3. So your final answer here will be 14 meters to the first. Now, I'm going to go ahead and explain the assignments, and you can get started after I do the explanation.